Discovery process, July 2025, 3I Atlas, the third object to enter the solar system from interstellar space, was discovered on the 1st of July 2025. The telescope of NASA-supported ATLAS, Asteroid Terrestrial Impact Last Alert System, survey project located in Rio Hurtado, Chile, was the first instrument to detect this new comet. As soon as the ATLAS team identified the object, they reported it to the Minor Planet Center, and the body, initially catalogued under the temporary code A10LP3Z, was officially designated C2025N1, ATLAS. After the discovery, an archival search revealed that various ATLAS telescopes and the Zwicky Transient Facility at the Palomar Observatory had already captured the object in pre-discovery images dating back to the 14th of June, 2025. This confirmed that the comet had been photographed weeks before it was actually detected. In the comet's name, ATLAS refers to the discovering project. The letter I stands for interstellar, and the number 3 indicates that it is the third interstellar visitor identified so far. 2. Determination of orbit and interstellar origin. Immediately after the discovery, orbital calculations revealed that this object follows a hyperbolic trajectory strong enough to escape the Sun's gravity. The orbital eccentricity of 3I Atlas exceeds 6, E6.14, and its hyperbolic excess velocity relative to the Sun was calculated as approximately 58 kilometers per second. This value confirms that its path is not a closed ellipse but an open hyperbola, meaning the object is not gravitationally bound to the Sun and will continue traveling into infinity. Indeed, in its initial observation report, the ATLAS telescope team noted that the object originated from interstellar space. 3I Atlas entered the solar system from the direction of the Sagittarius constellation, the same region where the center of the Milky Way is located. This approach direction and extraordinary speed, both unusual compared to any member of the solar system, led scientists to classify it as an interstellar object. With a velocity of about 245,000 kilometers per hour, approximately 68 kilometers per second, 3I Atlas became one of the fastest objects ever observed within our solar system. All these data provide strong evidence that the origin of 3I Atlas lies in a stellar system beyond our own Sun. From the physical properties, size, structure, and composition, size and structure, initial photometric estimates, made before the surrounding dust cloud, coma, was detected, suggested that 3I Atlas could be quite large. Assuming a low reflectivity, albedo, around 5%, calculations based on its brightness proposed a diameter of up to 20 kilometers. However, it was soon understood that the object was an active comet. As it approached the Sun, the heat caused sublimation of ices from its nucleus, releasing gas and dust to form a coma and a tail. Images taken by the Hubble Space Telescope, although unable to fully separate the nucleus brightness from the coma's light, indicated that the solid core was likely smaller than 1 kilometer in diameter. Thus, contrary to early expectations, 3I Atlas is not a giant object, but may have a nucleus typical in size for an ordinary comet. Its absolute magnitude, h, has been calculated as around 15.4, consistent with a dark, low albedo surface and a diameter of only a few kilometers at most. Structurally, 3I Atlas displays the familiar cometary form, an icy nucleus that heats up near the Sun, surrounded by a gas and dust coma, and a tail stretching away under the influence of the solar wind. In fact, images taken by ESA orbiters near Mars confirmed a distinct coma several thousand kilometers across. Photometric observations suggest that the nucleus rotates on its axis with a period of roughly 16 hours. Reflectivity and brightness. Due to its surface composition, 3I Atlas reflects sunlight inefficiently. Its albedo is estimated between 3 and 5%, possibly resembling a coal-black surface. Its visible brightness, therefore, arises mainly from light scattered by the active coma and tail. As a result, the object was never bright enough to be seen with the naked eye from Earth. Even at maximum brightness, it was only detectable through mid-sized telescopes. However, the comet's greenish hue, especially visible in photographs taken around September 2025, and the spectral lines recorded in its light revealed the presence of various gases in its composition, The chemical composition of 3I Atlas is one of the features that make it particularly interesting compared to previous interstellar objects. Spectroscopic data obtained from both ground-based and space telescopes detected a large amount of carbon dioxide, CO2 gas, in its coma. Observations by NASA's Next-Generation Space Telescope spherics confirmed the presence of abundant CO2 vapor in the coma and water ice within the nucleus, implying that 3I Atlas's structure significantly resembles that of comets within our solar system. Subsequent spectral data from the James Webb Space Telescope, collected on the 6th of August 2025, provided a more detailed chemical inventory. The coma contained water vapor, H2O, carbon monoxide, CO, some carbonyl sulfide, OCS, and an unexpectedly high abundance of carbon dioxide, CO2. The measured CO2-H2O ratio, about 8:1, is among the highest ever observed in any comet, far exceeding that of typical solar system comets at similar distances. This suggests that the nucleus of 3I Atlas may be unusually rich in carbon dioxide. Scientists have proposed several possible explanations for this anomaly. The object may have formed near the CO2 ice line of its parent star's protoplanetary disk, in a region dominated by CO2 ice rather than water ice. Its nucleus may have been heavily processed by cosmic rays or radiation, much more intensely than comets in our solar system. A thick insulating crust on its surface may prevent the easy sublimation of water ice. Even so, while CO2 dominates, the ratio of CO gas to water vapor was found to be relatively normal, around 1.4, similar to values observed in other comets, including 2I Borisov. This suggests that aside from its unusual carbon dioxide content, 3I Atlas may otherwise possess a fairly typical cometary chemistry. Additionally, spectroscopic observations made with the European Southern Observatory's Very Large Telescope detected cyanide, CN gas, and neutral nickel atoms in its coma. Interestingly, their abundance levels closely match those seen in solar system comets. Thus, while 3I Atlas stands out for its extraordinary carbon dioxide content, it still exhibits the familiar chemical fingerprints of common comets, such as toxic CN gas and metallic vapor signatures. 4. Approaching the solar system and orbital travel motion within the solar system. The movement of 3I Atlas within the solar system is particularly fascinating because it follows a highly inclined and retrograde orbit. When it was discovered in July 2025, the object was still about 4.5 astronomical units from the Sun, roughly around Jupiter's orbit, just entering the inner solar system. Its orbital inclination was measured to be approximately 175 degrees, meaning that 3I Atlas travels around the Sun in the opposite direction of the planets, along a path nearly perpendicular to the plane of the solar system. In other words, it entered the system from above the solar plane and moved downward through it. This extreme inclination is another indicator of its interstellar origin. Throughout the summer of 2025, the object moved rapidly inward. By September, it had approached the outer edge of Mars's orbit, passing its closest point to Mars on the 3rd of October 2025. However, close is relative. Even then, the distance between 3I Atlas and Mars was about 30 million kilometers. Although it technically crossed Mars's orbital path, it did not have a direct encounter. The minimum orbital intersection distance, MOID, for Mars was about 0.018 astronomical units. Its closest approach to the Sun, or perihelion, is calculated to occur on the 29th of October 2025. At a distance of roughly 1.36 astronomical units between Earth's outer orbital boundary and the inner edge of Mars's orbit, or about twice Earth's distance from the Sun. During this passage, the Sun's gravity will slightly bend its trajectory, but not enough to capture it. 3I Atlas will continue on a hyperbolic path, escaping once again into deep space after perihelion. A one-time visitor. This interstellar traveler's visit is a single flyby event. Because it is not gravitationally bound to the solar system, it will behave like a cosmic slingshot, gaining additional speed as it swings near the Sun before departing forever into interstellar space. Calculations show that 3I Atlas's velocity around the Sun will peak at approximately 68 kilometers per second by the end of October. With this immense speed, it is expected to move beyond Saturn's orbit sometime in 2026, and to completely leave the solar system within a few years. Orbital modeling also indicates that 3I Atlas has not experienced any significant past encounters with major planets, meaning its general orbital characteristics have remained largely unchanged since it first entered from interstellar space. Because it produces a substantial coma and tail, astronomers are also examining the non-gravitational forces acting on it, such as gas jets that can slightly alter its trajectory. However, unlike ʻOumuamua, no significant deviations have yet been observed. 3I Atlas appears to move primarily under the influence of gravity alone. 5. Close approach to Earth and risk assessments, distance and safety. The orbit of 3I Atlas keeps it at a considerable distance from Earth. Calculations indicate that this comet will approach no closer than about 1.6 to 1.8 astronomical units, roughly 240 to 270 million kilometers, posing absolutely no risk to our planet. NASA emphasized this point in its official discovery announcement, confirming that the object does not represent a threat and will remain at a safe distance. Compared to Earth's orbit, 3I Atlas will pass near the path of Mars, meaning that even its minimum distance from Earth will be almost twice the Earth-Sun distance. No threat to Earth. Therefore, 3I Atlas is not a near-Earth object, NEO hazard, but purely an object of scientific interest. The collision speculations often circulating in the media about large comets have not applied to this case. Since the orbital parameters were calculated with high precision within the first weeks of observation, all potential risk scenarios were ruled out early on. Moreover, because its mass and size are relatively modest compared to giant asteroids, the icy nucleus is estimated to be on the order of a few kilometers across. Even a hypothetical close approach would not pose a significant atmospheric danger. In reality, this remains purely theoretical, as 3I Atlas will pass far away from our planet on its interstellar journey. 6. NASA and ESA investigations and official statements. NASA's role. The discovery of 3I Atlas was announced as a success story of international cooperation in NASA's planetary defense and small-body research programs. In its statement on the 2nd of July 2025, NASA introduced the newly discovered interstellar comet, noting that it was detected thanks to the Atlas project, and that the first observations already suggested an interstellar origin. NASA experts emphasized the comet's hyperbolic orbit and highlighted how studying such visitors provides a rare opportunity to understand other stellar systems. The agency also invited the public to follow the comet's journey live through NASA's online tool, Eyes on the Solar System. Several observatories and research teams affiliated with NASA were mobilized for detailed studies. The Hubble Space Telescope observed 3I Atlas throughout July and August 2025, capturing high-resolution images that allowed the first direct estimates of the nucleus and coma. International teams working in collaboration with NASA also analyzed the object's spectrum using the James Webb Space Telescope, revealing unexpected compositional characteristics. In addition, NASA's Neil Gehrels Swift satellite carried out ultraviolet observations between July and August, detecting traces of water vapor, a first in the study of this object. NASA's active role throughout the discovery and research phase was communicated to the public through official press releases, social media channels, and outreach activities. ESA's contributions. The European Space Agency, ESA, responded rapidly to the 3I Atlas discovery, redirecting its resources to observe this unexpected interstellar visitor. During the first week of October 2025, ESA's ExoMars Trace Gas Orbiter and Mars Express spacecraft executed special maneuvers to observe the comet from their orbits around Mars. On the 3rd of October, these orbiters viewed 3I Atlas from a distance of about 30 million kilometers, successfully capturing coma images with their CASIS cameras. The images revealed a faint blurry coma several thousand kilometers wide, though the nucleus itself could not be resolved at that distance. ESA scientists noted that the Mars cameras were originally designed to photograph the planet's bright surface, making such a dim target extremely challenging to image. Despite this, data analysis continues, with teams studying the spectral data in hopes of detecting gases in the coma. ESA officials expressed satisfaction with the agency's ability to adapt quickly to such unexpected events and described 3I Atlas as a true alien from beyond our sun, emphasizing the scientific importance of examining it closely. Official statements. Both NASA and ESA underscored the scientific importance of 3I Atlas in their public communications. NASA's press releases adopted a reassuring tone, explicitly stating that the object posed no danger to Earth. ESA, in its reports, described 3I Atlas as possibly the oldest comet ever observed, suggesting that its orbit might have been wandering through the galaxy for billions of years, perhaps older than the Sun by as much as 3 billion years. Both agencies pointed out that this marks only the third recorded instance of such an event, following 1I ʻOumuamua in 2017 and 2I Borisov in 2019, making it a rare and thrilling moment in astronomy. ESA also reminded the public of its upcoming missions dedicated to studying interstellar visitors, such as Comet Interceptor, and noted that 3I Atlas has served as a direct inspiration for these future explorations. 7. Scientific research and analysis, spectrum speed, mass, ongoing scientific studies, and key findings since its discovery. Astronomers around the world have conducted numerous scientific studies to better understand the unique nature of 3I Atlas. Spectroscopic analyses, in particular, have yielded striking results. Spectroscopic discoveries. In August 2025, observations with the James Webb Space Telescope, JWST, revealed distinct emission lines of carbon dioxide, CO2, water, H2O, and carbon monoxide, CO, in the comet's spectrum. Data obtained through JWST's NIR-SPEC spectrograph showed that the coma of 3I Atlas was dominated by carbon dioxide. The observation, made at a distance of about 3.3 astronomical units from the Sun, still a very cold region, reported a CO2 to water ratio of approximately 8.0 plus 1.0. This ratio was statistically much higher than that of long-period or Jupiter family comets observed at similar distances, about 6 standard deviations above the mean. Based on these findings, Cordner and his team proposed that the ices in 3I Atlas's nucleus may have undergone a distinct chemical history. Possible explanations include the nucleus may have formed in a CO2-rich zone near the CO2 ice line of another star's protoplanetary disk, rather than in a water ice-dominated region. The object's structure may have been altered by intense cosmic ray bombardment during billions of years of interstellar travel. Its surface could have developed an insulating crust that limited water sublimation, while allowing CO2 near the surface to escape more easily. All of these scenarios remain hypotheses intended to explain the unusually high CO2 abundance, which continues to be tested through ongoing observations. Ground-based observations, ground-based telescopes also provided valuable insights into the comet's composition. Teams using the European Southern Observatory's Very Large Telescope, VLT, observed 3I Atlas between July and August 2025, detecting key molecular signatures in its spectrum. The VLT data revealed cyanide, CN, molecules and neutral nickel, Ni atoms in the gas emitted from the comet. This discovery was highly significant because CN gas and trace amounts of heavy elements such as iron and nickel are also known components of typical solar system comets. In fact, nickel had also been detected in the interstellar comet 2I Borisov. The detection of CN and Ni in 3I Atlas shows that chemically, it is not radically alien. Its surface composition shares similarities with comets native to our solar system. This provides crucial evidence that interstellar objects are not necessarily made of entirely foreign materials. Velocity and mass findings. The inbound velocity of 3I Atlas upon entering the solar system was calculated as approximately 58 kilometers per second. Its hyperbolic excess velocity, v, relative to the Sun. This tremendous speed reflects its natural orbital motion within the Milky Way and aligns with the typical random velocity distribution of objects within the galactic disk. If non-gravitational effects such as gas jets do not significantly alter its path, the object's trajectory shows no major deceleration. While scientists cannot directly measure its mass, estimates based on a nucleus smaller than 1 kilometer and an icy rocky composition suggest a total mass in the order of billions of tons. For instance, a 1-kilometer comet nucleus with a density of about 0.5 grams per cubic centimeter would have a mass around 10 to the 12th to 10 to the 13th kilograms. The Neil Gehrels Swift satellite's ultraviolet observations showed that in July 2025, 3I Atlas was losing about 40 kilograms of water per second. Even with this rate, roughly 3.5 million kilograms per day, the total mass loss over several months would be negligible compared to its total mass, around 1,000th of 1%. Hence, the comet is expected to retain most of its material as it exits back into interstellar space. Rotation and light curve. Analysis studies of 3I Atlas's rotation period have also been carried out. Light curve analyses of its brightness variations indicate that it rotates around its axis once every approximately 16 hours. Observations from the Gran Telescopio Canarias and other observatories in July 2025 reported a consistent period of 16.16 plo for 0.01 hours. The brightness variation amplitude was low, only about 0.2 magnitudes, which is consistent with the idea that the nucleus's intrinsic light fluctuations are masked by the bright and active coma. The continuous emission of gas and dust from all sides tends to smooth out brightness differences caused by surface irregularities or albedo variations, galactic. Origin studies efforts have also been made to trace the galactic origin of 3I Atlas. In a study published in September 2025, astronomers retraced its trajectory 10 million years into the past to determine whether it passed near any stellar systems. Using Gaia mission data on stellar positions and motions, they found that 3I Atlas had relatively close encounters, on astronomical scales, with about 62 stars during its journey. But none of these significantly affected its velocity or direction. This suggests that the object has likely been traveling alone through space for millions of years, having been ejected from a parent star system long ago. Orbital analyses indicate that it probably originated from the region of the Milky Way known as the thin disk. Initially, some researchers proposed that its slower galactic velocity implied it might belong to the thick disk population, home to older stars, making it possibly more than 7 billion years old. However, more recent analyses found its motion to be more consistent with the thin disk, suggesting it might be relatively young on galactic timescales, perhaps as old as, or slightly older than, our Sun. Conclusion in summary. The scientific investigations into 3I Atlas have painted a rich and complex picture of its dynamic, physical, and chemical characteristics. The comet combines both surprising traits, such as its extreme CO2 abundance, and familiar ones, such as CN presence, dust structure, and rotation behavior. Together, these findings mark 3I Atlas as a rare but deeply informative interstellar messenger, bridging the gap between our solar system and the wider galactic environment. 8. Public reaction and media interest. Public and media reaction to the discovery of 3I Atlas. From the moment it was discovered, 3I Atlas captured not only the attention of scientists but also the curiosity of the global public, quickly becoming a popular astronomical phenomenon. Mainstream media and popular science outlets brought widespread coverage to the story of this interstellar comet. Platforms such as Space.com, EarthSky, and numerous astronomy magazines published detailed articles explaining its significance and ongoing observations. These reports emphasize that 3I Atlas was the third interstellar visitor ever detected, following ʻOumuamua in 2017 and 2I Borisov in 2019, and framed it as part of an emerging pattern of interstellar encounters. The media frequently compared 3I Atlas to its predecessors, helping the public understand its place in a broader scientific context. These comparisons are discussed further in Section 9. The public's fascination grew even more when NASA and ESA released official imagery. In particular, a striking color photograph published by Neuer Lab Gemini Observatory in September 2025 showed 3I Atlas with a bright green coma and a long glowing tail. The image spread rapidly across news outlets and social media, powerfully reinforcing the idea of a visitor from another galaxy. Speculations and controversies, as with any high-profile astronomical discovery, 3I Atlas also sparked more speculative interpretations, echoing the debates that began with ʻOumuamua. Some questioned whether the object might represent alien technology. In July 2025, Harvard astrophysicist Avi Loeb and his collaborators published a preprint on Archive titled, "Is 3I Atlas an Alien Technology?" suggesting hypothetically that it could be an artificial probe. Although the paper had not undergone peer review, it received substantial attention in the press and online communities. Certain media outlets amplified Loeb's claims with sensational headlines portraying 3I Atlas as a potential alien spacecraft. Loeb's team speculated that the object's orbital alignment, passing strangely close to the orbital planes of Venus, Mars, and Jupiter, might hint at deliberate trajectory tuning. In reality, 3I Atlas remained hundreds of millions of kilometers from those planets, though its orbital plane indeed intersected theirs at narrow angles. Discussions about how one might identify a genuine extraterrestrial probe, such as detecting artificial radio signals or observing deliberate course corrections, also appeared across forums and science commentary sites. Scientific consensus: a natural comet. Despite these speculations, the scientific consensus remains clear. 3 Atlas is entirely natural. The object's visible tail and coma are unmistakable evidence that solar heating is causing its icy materials to sublimate. Classic cometary behavior. Publications like Sky at Night magazine released articles with headlines such as, "Our solar system's interstellar visitor is definitely not alien, here's the evidence." These articles cited the absence of artificial radio emissions, lack of self-propelled motion, and a chemical spectrum perfectly consistent with natural cometary ices. Public engagement and education. From a public perspective, the 3I Atlas event became both a source of wonder and an educational moment. For many people, it was the first time they encountered the concept of interstellar objects, bodies arriving from beyond our solar system, and the realization that pieces from other stars can travel through our sky. Captivated imaginations. Worldwide, astronomical organizations and space agencies worked to harness this enthusiasm through outreach initiatives. For example, under NORLAB's Shadow the Scientist program, a live-streamed observing session was held in August 2025 from the Gemini South telescope. During the broadcast, viewers could watch real-time data collection of 3I Atlas, ask questions, and interact with astronomers via video link. Students from Hawaii and Chile joined the session virtually, experiencing firsthand how telescopes are operated and how data is gathered. These events transformed 3I Atlas from a mere news headline into a participatory science experience, inviting the public into the process of discovery itself. Conclusion: ultimately, the public response to 3I Atlas painted a vibrant picture, a blend of grounded scientific curiosity and occasional speculative fascination. The comet's visit served as a bridge between professional astronomy and public imagination, reminding the world that the universe still holds surprises arriving from far beyond our sun. 9. Comparison with previous interstellar visitors: 1I ʻOumuamua and 2I Borisov. Comparison with other interstellar visitors: 1I ʻOumuamua and 2I Borisov is the third identified interstellar object in history. 3I Atlas holds a special place in astronomy, inviting direct comparison with its two predecessors: 1I ʻOumuamua, discovered in 2017, and 2I Borisov, discovered in 2019. Examining the similarities and differences among these three travelers helps scientists understand just how diverse interstellar objects can be. ʻOumuamua, the enigma of 2017, discovered in October 2017. ʻOumuamua became the first confirmed interstellar object ever detected, instantly captivating the scientific community. Its shape and behavior were extraordinarily puzzling. Despite being small, about 100 to 150 meters in length, it showed irregular brightness variations and, intriguingly, no visible coma or tail. Initially classified as an asteroid, ʻOumuamua later surprised scientists by exhibiting a non-gravitational acceleration while moving away from the sun, without any visible gas emission. Some researchers suggested that this could be caused by radiation pressure on a thin structure, even proposing the speculative idea of a solar sail. Others argued it might result from sublimation of invisible volatile ices such as hydrogen or nitrogen. By contrast, 3I Atlas behaves as a textbook comet, clearly releasing gas and dust when heated by the sun, forming both a coma and a tail. Where ʻOumuamua appeared dry, 3I Atlas is distinctly wet, Orbital parameters also differ markedly. Oumuamua traveled at about 33 kilometers per second with an inclination of roughly 123 degrees, whereas 3I Atlas races through the solar system at nearly 58 kilometers per second on an almost fully retrograde orbit, inclined at about 175 degrees. Oumuamua passed much closer to the Sun, about 0.25 astronomical units, but was discovered too late, only after it had begun to leave the inner solar system, allowing for just a few weeks of observation. In contrast, 3I Atlas, although never approaching closer than about 1.4 astronomical units, was detected months in advance, enabling extended study. In terms of size, Oumuamua was perhaps 1/10 the diameter of 3I Atlas's nucleus, making 3I Atlas far brighter and easier to observe, earning it the distinction of being the largest and brightest interstellar object ever recorded. Borisov, the true comet of 2019, the second interstellar object, 2I Borisov, was discovered in August 2019 by amateur astronomer Gennady Borisov in Crimea. Borisov resembled a classic comet, much like 3I Atlas, a small nucleus roughly 0.4 kilometers wide, surrounded by a coma and tail composed of gases such as cyanide, Cn, and diatomic carbon, C2. Its chemical composition closely matched that of solar system comets, though it stood out for its high carbon monoxide CO content. Spectroscopic measurements revealed that Borisov's CO to H2O ratio exceeded that of most local comets, suggesting formation in the cold, outer regions of its home system. Our Atlas shows a similar anomaly, but instead of CO richness, it exhibits CO2 enrichment. Thus, one might summarize, Borisov is CO-rich, while Atlas is CO2-rich. Aside from this difference, 3I Atlas appears somewhat larger and more active. Borisov's brightness peaked around magnitude 15 at the end of 2019, while 3I Atlas reached comparable brightness in 2025 but remained observable for a longer period, due to its slower change in solar elongation and favorable visibility from southern hemisphere. Observatories both comets displayed characteristic CN lines in their spectra and shared color properties with solar system comets. In terms of dynamics, Borisov traveled at a hyperbolic velocity of about 32 kilometers per second, whereas 3I Atlas moves at around 58 kilometers per second, suggesting that it may originate from a more energetic galactic orbit. Together, Borisov and Atlas provide the clearest evidence yet that interstellar comets truly exist and can exhibit the expected dirty snowball behavior. Borisov offered the first proof that such an object could resemble our own comets, while Atlas added new complexity with its distinctive chemical makeup. A broader perspective on interstellar diversity, considering all three known interstellar objects together, Oumuamua, Borisov, and Atlas, one key conclusion emerges. Interstellar visitors are highly diverse. Each has surprised scientists in different ways. As Dr. Zexi Xing of Auburn University aptly summarized, every interstellar comet so far has managed to surprise us. Oumuamua turned out dry, Borisov was rich in carbon monoxide, and now Atlas is releasing water and carbon dioxide from an unexpected distance. This diversity reflects the variety of planetary formation conditions across different stellar systems. Yet there are also unifying themes. Both Borisov and Atlas display the same fundamental physical processes as solar system comets: sublimation of ices, coma formation, and tail development, reinforcing the universality of cometary physics across the galaxy. Finally, these discoveries confirm long-standing theoretical predictions. Astrophysicists had expected that interstellar space should be filled with countless such wanderers, statistically implying that at any given time, one could be passing through our solar system. Even before Oumuamua and Borisov were detected, models had predicted that sufficiently sensitive telescopes would eventually find them. The discovery of 3I Atlas has now validated those forecasts and suggests that many more interstellar visitors may soon be revealed. 10. Current status, October 2025, and future observation plans, current status and future prospects of 3I Atlas figure. In a deep exposure image taken on the 27th of August, 2025 by the Gemini South Telescope, the interstellar comet 3I Atlas appears with a bright central nucleus surrounded by a vast coma and a faint tail extending opposite the direction of the solar wind. Because the telescope's tracking was locked to follow the comet's motion, the background stars appear as streaks rather than fixed points. Within the coma, a dense dust cloud is clearly visible, while the faint tail spreads over an angle of roughly 1/120th of a degree. Two small, colorful streaks in the frame belong to unrelated passing asteroids. Approaching perihelion as of October 2025, 3I Atlas is nearing its closest approach to the Sun. On the 29th of October, it will reach perihelion at a distance of approximately 1.36 astronomical units, roughly between the orbits of Mars and Earth. Currently, its position near the Sun makes ground-based observation difficult. Since late September, the comet has been lost in the Sun's glare, entering an observational hiatus. Throughout November, it will remain too close to the Sun for direct observation, but astronomers expect it to re-emerge from behind the Sun in early December 2025. During this phase, telescopes worldwide will attempt to capture it again. The comet's brightness is expected to increase slightly after perihelion as solar heating intensifies its gas and dust emission. New observation campaigns are already planned. Hubble Space Telescope and possibly JWST, James Webb Space Telescope, will focus on the comet in December and early 2026 to study potential changes, such as signs of fragmentation or shifts in chemical composition. Ground-based observatories like VLT and Gemini North will continue tracking it once it becomes visible again from the northern hemisphere. Departure from the solar system throughout 2026. 3I Atlas will gradually recede and fade from view, likely becoming invisible even to amateur telescopes by mid-year. Yet the legacy of this interstellar traveler extends far beyond its brief visit. Its passage has galvanized the scientific community to prepare for future encounters with similar objects. The upcoming Vera C. Rubin Observatory, formerly LSST, with its vast sky surveying capability, is expected to dramatically increase the detection rate of such interstellar visitors. Some models predict that these wanderers may be among the most common types of objects in the Milky Way, implying that one could be passing through our solar system at almost any given time. Rubin's all-sky coverage could potentially detect dozens of interstellar objects within the next decade. This prospect excites astronomers and motivates space agencies to plan rapid response missions capable of intercepting such bodies. Future missions, Comet Interceptor and beyond. European Space Agency's Comet Interceptor mission, scheduled for launch in 2029, is a major step in this direction. The spacecraft will wait in a parking orbit near the Earth-Sun system, ready to redirect toward any newly discovered pristine comet or, ideally, an interstellar object like 3I Atlas. Since the discovery of ʻOumuamua, ESA's Comet Interceptor team has been preparing for such an opportunity, emphasizing how a close-up encounter with an interstellar body could revolutionize planetary science. However, agency officials also acknowledge the extreme difficulty of intercepting a fast-moving target. Realistically, the chance of catching an interstellar object in the near future remains low. Still, Comet Interceptor will serve as a pathfinder, representing the first mission designed to await and chase a yet unknown interstellar visitor. NASA has likewise conducted feasibility studies for similar rapid response concepts. Projects like Project Lyra, proposed after ʻOumuamua's discovery, explored ultra-fast launch options for intercepting interstellar bodies. Other ideas, such as redirecting existing spacecraft like New Horizons or Parker Solar Probe toward 3I Atlas, were evaluated but deemed unfeasible due to velocity and trajectory constraints. Even so, data gathered from 3I Atlas are shaping our understanding of what will be required to successfully pursue future interstellar targets. Scientific legacy. In the months since its discovery, 3I Atlas has provided profound insights into the nature of interstellar comets and deepened our understanding of planetary formation and chemical diversity beyond the solar system. Now, as it speeds away, never to return, it stands as a tangible reminder that our solar system is not isolated in the cosmos. Fragments from distant stars continue to pass among us, carrying with them the chemical stories of other worlds. The lessons learned from 3I Atlas will guide future exploration and observation, ensuring that when the next interstellar traveler is found, humanity will be ready. This ongoing search for visitors from beyond keeps alive one of astronomy's oldest motivations: the desire to know what else, and who else, might be out there.